Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Jest, Tifr, IIT-Jam and other exams related to physical science. Okay, so this is the 8th part of the series in which we are doing CSIR NET Physics PYQs of December 2019. Okay, so I'm going to start, and also I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. Okay, so I'm going to start now with question number first. Question is, the phase difference. This is the question from interference, guys, okay, which I have already taught in my Sunday special class. I have taught in detail. Okay, so the phase difference, the phase difference, the phase difference between two small oscillating electric dipoles separated by a distance d, small d, is pi if the wavelength of if the wavelength of the radiation is lambda, the condition for constructive interference between the two dipolar radiations at a point P when R is greater equal to D. Symbols are as shown in the figure. And n is an integer. n is an integer. n is an integer, is okay, and options are d sine theta equal to n plus half lambda. Option B is d sine theta equal to n lambda, d sine theta equal to n lambda. Option C, d cos theta equal to n lambda, and option D is d cos theta equal to n plus half lambda. Okay, and the figure is also given. Figure is these are two dipoles given which are in opposite phase. Okay, this is the point P. Okay, this is the point P. This is the point P, and this angle is given theta, and these are two dipoles. This is origin O. Okay, and this distance between two dipole is D given, and this distance is R, where R is greater equal to D. Okay, so this is the question given, guys. I'll solve it now, but before that, let me just check whether I'm audible or not. Okay, then I'll proceed further. As shown in the figure, yes, I'm audible, so I'll proceed further. Okay, so this is the figure which is given. So this is the interference question. Okay, I'll make a figure now for solution. And I'm going to do it in next page. Okay, I'll make a figure. This is point O, and this is the dipole. Okay, there is a dipole and there is a dipole, and this distance is d by 2 and d by 2, because the total distance is d, and this is the midpoint. Okay, and at this point here we need to find out interference. Okay, condition for interference. So we can do like this. Can do like this. There's a point. Okay, and this is like this. This is dipole. Okay, these are dipoles, and this is the distance between from origin. Yeah, this angle is theta. This is given, right? This angle is theta. This distance is r. This distance is r. Okay, suppose this distance is r1. This is r1 and this is r2. Okay, this is the point P, and these are the dipoles. which is given 12. And this is the path difference, right? And this is also path difference. This angle is 90, right? This is 90 minus theta. This angle is also going to be theta, right? And this is the perpendicular. So the path difference for this distance is going to be d distance from here to here, right? This is going to be d by 2 sine theta, right? This distance is going to be, suppose this is x and this is y. Okay, ox is going to be, that is d sine theta, right? This is d sine theta. D sine theta. This is similarly here by symmetry. This angle is also going to be theta, and this distance, suppose this is this distance from here, this distance is going to be again d sine theta. This is a 90 angle, right? And this is the height, and this is the base, and we know sine theta equal to height upon hypotenuse, right? So so this value is going to be, we can say this value like m and n. Okay, so ym is going to be d by 2 sine theta. Similarly, this ox is going to be d by 2 sine theta. Okay, so from here we can also, this is also here, this is going, r value of r1 is going to be, this is r, right? So this we can write this one, d by the ym plus op, right? This is same, right? So so this is going to be r plus, understand this question very carefully, guys. Okay, so this is going to be r plus d by 2 sine theta. Similarly, and this r2 is going to be this r minus this one, right? So r minus d by 2 sine theta. Okay, so from here we can easily find out phase difference, right? Phase difference is going to be r1 minus r2, so that is r plus d by 2 sine theta minus r minus minus plus d by 2 sine theta. R will get cancelled, and this is going to be d sine theta. So this is the path difference, right? We can write delta. Delta is d sine theta. Okay, so delta is d sine theta. D sine theta. Okay, d sine theta. So now this is d sine theta. This is the delta value, that is d sine theta. Okay, and also in question it is given, guys. What is given? This is, I'll show you. The phase difference between two small oscillating dipoles separated by distance d is pi, right? So you can see here, I'll figure, this is the direction is different, right? The phase difference is pi by, the phase difference is pi, right? So we can write the we know the path difference, that is phase difference delta phi is going to be 2 pi by lambda into path difference delta, right? This we know. And we have got the path difference for these two radiation. Okay, these are dipolar radiation, because this radiation is from here. These dipoles are producing the radiation. Okay, these dipoles are source of radiation. At point P, we have to find out the condition for constructive interference. Okay, so so from here, delta phi is going to be this because we can see since dipoles are in opposite direction, so initial phase difference is pi. Okay, so this is going to be, this value is going to be delta phi plus pi, and this value is 2 pi by lambda into delta. This we know, right? Phase difference is 2 pi by lambda into path difference. Okay, very important point. So delta phi value is 2m pi, okay, plus pi is going to be 2 pi by lambda into d sine theta. Okay, pi will get cancelled, and this is 2n plus 1 upon 2 we will take here. Okay, so this is going to be d sine theta d sine theta upon lambda, right? So here this is going to be n plus half. Okay, lambda will take this side, is going to be d sine theta, right? So d sine theta imply d sine theta equal to d sine, these are part C question, guys. Okay, d sine theta equal to n plus half lambda. Okay, which option is matching, guys? Let me check. Option A is matching, guys, right? This one, option A. D sine theta equal to n plus half lambda. D sine theta equal to n plus half lambda. This is the answer, guys. It's just a geometry, guys, so we should know, we have to just get the part difference, and then we know phase difference equal to 2 pi by lambda into part difference. Because dipoles are in opposite direction, so phase difference is going to be, so they will be because their initial phase change will be, phase difference will be pi, because they are in opposite direction. So the phase difference is going to be delta phi plus pi. Okay, and delta phi value is 2n pi, and this, and we've got the connection. Okay, very good question, guys. I hope you understood it. Next question. Okay, next question is it is also a very good question, very but it's a complicated, but you can easily solve it. I'll tell you the procedure for solving this question. Okay, it is a very long integration actually. Okay, so question number 2 is the Hamiltonian of two particles Hamiltonians of two particles, each of mass m, is h is given. Okay, which is function of q1, p1, q2, p2. Okay, this is given. Okay, so this is p1 square upon 2m plus p2 square upon 2m plus k into q1 square plus q2 square plus 1 upon 4 q1 q2. Okay, q1 q2, where k is greater than 0 is a constant. The value of part C question, guys. Okay, these are part C questions of December 2019 we are solving. So the value of the partition function ZB equal to integration minus infinity to plus infinity, that is q d1 q qd1 qd1 sorry d my apology, it's dq1 guys, okay, dq1 into integration minus infinity to plus infinity dp1 dp1 into integration minus infinity to plus infinity dq2 dq2 into integration minus infinity to plus infinity dp2 dp2 e to the power minus beta h minus beta h, okay, h is Hamiltonian, okay, which is function of q1 q2 and p1 p2, right, or p1 the same thing, okay, okay, or q1 p1 q2 p2 or q1 q2 q1 p2, same thing, okay, into is this value is, okay, partition function, this value you need to find out, and options are given guys. Options are option A 2 pi m square upon k beta square root 16 upon 15 root 16 upon 15 root 16 upon 15. Option B is 2m pi square root 15 upon root 15 upon 16 upon k beta square. Option C is 2m pi square upon k beta square root 63 upon 64, and option D is 2m pi square upon k beta square root 64 upon 63. Okay, so this is the question guys. Okay, so I'm going to solve it now. So partition function which is ZB, okay, function of beta is we can write here, okay, so this is going to be minus infinity to plus infinity dq1 into minus infinity to plus infinity dp1 into minus infinity to plus infinity dq2 into minus infinity to plus infinity dp2 e to the power minus beta. We'll put the value of h guys, okay, h value we know, which is given here. This is p1 square upon 2m plus p2 square upon 2m plus this, okay, so this is going to be p1 square upon 2m okay, so this is going to be e to the power minus beta p1 square upon 2m plus p2 square upon 2m plus plus k into q1 square q1 square plus q2 square plus 1 upon 4 q1 q2, right? This is the e to the power, right? So we can write this integration minus infinity to plus infinity, and this is going to be e to the power minus beta p1 square upon 2m dq1 dp1 sorry dp1 okay, and integration we can write like this: minus infinity to plus infinity e to the power minus beta p2 square upon 2m okay dp2 into integration minus infinity to plus infinity e to the power minus beta k, and this is going to be q1 square plus q2 square plus 1 upon 4 q1 q2 okay, this is, and then it's dq1 into dq2 guys, okay, this one. So we know the formula, right guys? Here we have a formula. So e to the power minus, this I have already explained in my mathematical class as well yesterday. So e to the power minus beta x square, okay, beta or alpha x square. Alpha is a constant, so here we can see e to the power minus alpha is constant is beta upon 2m p1 square dp1, okay. This we know, integration minus infinity to plus infinity e to the power minus alpha x square. This alpha x square dx is going to be, this I have already explained yesterday. So this value is in my variational principle, variational method class of quantum mechanics also I have explained this. Okay, so this value is going to be root pi upon alpha. So here alpha is beta upon 2m, right? Okay, and p1 square into p1, right? So we'll use this formula here. Okay, so this is going to be root pi upon beta upon 2m into root pi upon beta upon 2m, okay. And this integration guys, this is very lengthy integration, right? And I would request you, don't try to solve this integration in examination. It will take long time, okay, it will waste your time. So I would suggest you just note down this integration and memorize it, okay guys. It's minus infinity to plus infinity e to the power minus beta k, any constant, q1 square plus q2 square plus 1 upon 4 q1 q2 into dq1 dq2. This integration is, this you need to note down, and this is guys, this integration is this is pi upon beta k, okay. This is pi upon beta k, okay, pi upon beta k, this beta k, okay, pi upon beta k into 64 upon 63. This you need to note down, right? Okay, for this very lengthy integration, so I would suggest you to note down pi upon beta k. This is the beta it will, okay, pi upon beta k root 64 upon 63. Now we can solve it. So this is going to be, this value is going to be beta these are in roots, right? So this is going to be pi upon beta 2m, so 2m pi upon beta, right? This value is 2m pi upon beta, 2 pi m upon beta, z beta equal to, okay, z beta 2m pi upon beta, 2m 2m pi upon beta into this value, pi upon beta k, pi upon beta k, root 64 upon 63. Okay, root 64 upon 63, and this is going to be z, which is function of beta. Okay, this value is going to be now 2m pi square upon beta square k, 2m pi square upon beta square k into 64 upon root 64 upon 63, right? This is the answer. Okay, so note down this integration. We know this integration is it's a very lengthy integration, so I would suggest you to note down and memorize this value. Okay, root pi upon beta k. Okay, pi upon beta k, root 64 upon 63. Okay, okay, so we have put the value and we've got the answer. So which option is matching, guys? Option D is matching. 2m pi square upon k beta square, 2m pi square upon k beta square into root 64 upon 63. Okay, guys, so option D is the correct option. Next question, guys, it's a very good question. This question is from condensed matter physics, superconductivity. Okay, which I'm going to solve now. Okay, question number third. Question number third is, in AC Josephson effect, in the AC Josephson effect, in the AC Josephson effect, a supercurrent flows across two superconductors okay, so flows through, the superconductor flows across two superconductors separated by a thin insulating layer and kept at an electric potential at an electric potential difference delta V. The angular, very simple question, okay, formula based. The angular frequency angular frequency of the resultant supercurrent is given by the angular frequency of the resultant supercurrent is given by options are given. Option A, 2 rho delta V. In question it is given E, guys, but rho is the correct one. Okay, so I'm writing the correct one. 2 rho delta V upon H cut. Option B is rho delta V upon H cut. Option C is rho delta V upon pi H cut. And option D is rho delta V upon 2 pi H cut. Okay, so this is the question. The question is, in AC Josephson effect, a supercurrent flows through two superconductors, okay, separated by a thin insulating layer, okay, and kept at an electric potential difference delta V. The angular frequency of the resultant supercurrent is given by. Okay, so angular frequency of the resultant supercurrent we need to find out. Okay, so I'll make a diagram, then it will clear your doubt. Okay, so okay, these are two superconductors which are attached, separated by thin insulating layer. Okay, this is thin insulating layer, very thin insulating layer. Okay, and okay, and layer, and kept at an electric potential difference delta V. Okay, so electric potential difference delta V. Okay, okay, this is delta V, electric potential difference delta V. Okay, this is given, and this is thin insulating layer. Okay, and now we need to find out the angular frequency of the resultant supercurrent. Okay, resultant supercurrent. Okay, so we know there is a formula, right? We know J equal to that current density through insulating layer. Okay, J is current density through thin insulating layer. Current density through thin insulating layer. Current density through thin insulating layer. Okay, that is J. J is, we know J is, this is J naught delta 0 minus omega t. Okay, this is the value of this current density through insulating layer. Current density through insulating layer is J equal to J naught delta 0 minus omega t. Okay, and where the value of omega, the angular frequency of supercurrent, that is omega, that is angular frequency of supercurrent value is 2 rho delta V upon H cut. Okay, this you need to note down, guys. So J equal to, and memorize, J equal to J naught delta 0 minus omega t, and omega t value is 2 rho delta V. This is the potential difference, 2 rho delta V upon H cut. Okay, 2 rho delta V upon H cut. Okay, so this is the answer. And which option is matching? Option A is not matching. 2 rho delta V upon H cut. This is very simple question of 5 marks question. Okay, well, so this is the one. So this is J equal to J naught delta 0 minus omega t, and value of omega is 2 rho delta V upon H cut. Okay, for AC current, 2 rho delta V upon H cut. Well, so this is the question, simple question, guys. Next question is, it's a good question, guys. The negative neon a negative neon uh, a negative neon a negative which has nearly 200 times a negative neon which has a mass which has a mass nearly 200 times that of an electron replaces an electron in a Li atom okay, that replaces the electron in a Li atom, that is lithium atom. Okay, the lowest ionization energy lowest ionization energy for the muonic lithium lowest ionization energy for the muonic lithium atom is approximately options are given. Option A is this the same as approximately the same as that of helium. Okay, option B is the same as that of normal Li atom. Okay, and option C is 200 times larger than 200 times larger than that of normal Li, and option D is the same as that of as that of normal B, beryllium. Okay, so this is the question, guys. I'm going to solve it. So question is a negative muon, okay, which has a mass nearly 200 times that of electron, okay, whose mass is 200 times greater than the electron nearly, okay, replaces electron in the lithium atom, okay. In lithium atom, that electron is replaced by that muon, okay. The lowest ionization energy for muonic lithium atom, okay, the lithium atom in which muon is there instead of lithium is approximately same as that of helium, okay, or same as that of normal lithium, or 200 times larger than that of normal lithium, or same as that of normal beryllium, okay. This is the question. I'm going to solve it now. Okay, so I'll tell you the formula for ionization energy, okay. So ionization energy I, ionization energy I value is RC. I'm going to write directly, okay. So RC, okay, so this is RC R infinite, at least you should know, okay, RC R infinity upon N square Z minus S whole square M dash upon M, okay, or you can write I equal to, you need to note down this one only, okay, A M dash upon Me, okay, this is mass of electron, M dash upon Me, okay. So, note down this one, okay, this is going to, this formula is helping you, okay, for solving question, okay, this one. So M dash upon Me, right? So M dash is that is reduced mass, okay. So now we will find out the reduced mass for M dash for normal lithium atom, okay, normal Li atom, okay. So this is going to be M dash equal to, we know, right, this is 7 MP, that is proton, 7 MP into Me mass of electron upon 7 MP mass of proton, because the atomic number of lithium is 7, okay, plus Me, right. So this is going to be 7 into mass of proton is 1836 times mass of electron, right. So mass of electron into mass of electron, right, upon, this is going to be 7 into 1836 mass of electron plus Me, right. So Me will get cancelled, so this is going to be this one. So Me will get cancelled, so value of M dash upon Me, this Me will take in this side, so this is going to be 7 into 10 to the 7 into 1836 upon, this is going to be 7 into 1836 plus 1, this is very small value, right, plus 1, right, and this value is going to be almost equal to 1, right, this is just 1, this value is just this is that, right. So this value is going to be just equal to 1. This is a very huge value, or we can just leave that 1, right. So this value is going to be 1, so this value is almost, we can say, 1, okay. So it means the ionization energy I1 for normal lithium is going to be A into 1. Okay, so that is almost equal to A. Similarly, I2 ionization energy for this is going to be A into M2 M dash upon M E, right? A into M dash upon, my apology, this is A into M dash upon Me, right? This one. And because ionization value formula is this, okay? So this I2 is, so now we'll find out value of M dash, okay? M dash. So M dash value is going to be reduced mass of M dash. Now there's a lithium instead of electron. So this is going to be 7 MP into lithium, okay? Muon is there, right? So this is going to be, this is 200 times of Me, okay? And 7 MP upon, this is going to be 700 MP into 700 MP plus 200 MP plus 200 Me, right? So this is going to be 7 into 1836 Me square, right, upon this one. 7 into 1836 plus 200 Me, right? Because MP equal to mass of proton is 1836 times mass of electron, right? I have just put the value, right? So this means M dash upon for lithium atom, okay? I2 is for lithium, for muonic lithium atom. So this M dash value is going to be M dash upon Me will get cancelled, 1 Me will remain, right? And that will take in the denominator of M dash. So M dash upon Me is going to be 7 into 1836 upon 7 into 1836 plus 200, and here 200 as well, right? This 200 into 200 into 200 Me square, right? Me will get cancelled, 1 Me, right? And this value into 200, and this value is almost equal to 197, okay? So 197 A is there, right? A is there, A, right? So you can see I2 equal to 197 A and I1 equal to A, right? And I1 equal to A, so we can say I2 equal to 197 I1, or I2 is almost 200 times of I1, right? So which option is matching, guys? Option C, 200 times larger than that of normal lithium atom, okay? So I2 is the ionization energy of muonic lithium atom, right? So you can see this is 200 times of I1. I hope you understood it, guys, okay? I hope you have understood it, okay? Next question. Next question is, this is also a good question, okay? Question number 5. The wave function of a particle of mass m constrained to move in a circle, on a circle of unit radius of unit radius of unit radius of unit radius unit radius centered at origin, centered at the origin, centered at the origin in xy plane is described by psi phi equal to psi, which is function of phi, equal to a cos square phi, where phi is the azimuthal angle, azimuthal angle. All the possible outcomes, all the possible outcomes of measurements of LZ, that is Z component of angular momentum, right? LZ in this state in units of h cut r. Okay, options are A plus minus 1 comma 0, and option B is plus minus 1, option C is plus minus 2, and option D is plus minus 2 comma 0. Okay, this is the question, guys. Okay, so the wave function for a particle of mass m is given, which is constrained to move on a circle of unit radius at centered at origin, whose center is at origin in xy plane, is described by wave function psi phi equal to a cos square phi, where phi is the azimuthal angle. Okay, the all possible outcomes of measurements of LZ, okay, that is Z component of angular momentum in this state in units of h cut r. Okay, that's you need to find out. Okay, so simple question, and I'll tell you how to solve this question. Okay, so we have been given psi phi is given, that is a cos square phi, right? This is given. So we can write like this: a cos square phi we can write, because we know cos 2 theta equal to 2 cos square theta minus 1, right? So here we can write cos square theta value is going to be cos 2 phi plus 1 by 2, right? Or we can write a by 2 into cos 2 phi plus 1, right? We can write like this, and so, or we can write psi phi. Okay, and we need to find out this all the possible outcomes of measurements of Z component of angular momentum, that is LZ. Okay, so phi is going to be very simple, just you need to know it procedure. So cos 2 phi we can write e to the power iota 2 phi plus e to the power iota minus iota 2 phi by 2 plus 1, right? We can write cos phi is like this. Okay, and also we can write one value of 1 e to the power iota 0 phi. We can also write e to the power iota 0 phi, right? We can write it, because e to the power iota 0 phi value is 1, and cos 2 phi values e to the power iota 2 phi plus e to the power minus iota 2 pi by 2, right? So from here, right, we can directly write the value of the all possible outcomes of z. Okay, these are going to be the coefficient of this coefficient of iota. Okay, so these are iota 5, iota 5. Okay, coefficient of iota 5. We can write like this. This will be better. This is going to be e to the power 2 iota 5 plus e to the power minus 2 iota 5, and this is e to the power minus 0 iota 5, minus 0 iota 5. Okay, so this from here directly we can tell the values of them. Those are coefficient of iota 5, iota 5. So these are 2, minus 2 and 1, 0, right? This is how you can solve this question easily. Okay, these are the answers. So 2 minus 2, 0. So which option is matching, guys? D. Plus minus 2, 0. Okay. Well, guys, so I'll stop here, and before